I get the kilos, 50%. If you are not bilingual, get the fuck up out of town before we run your ass down. Underground, how I came out. Any nigga try to stop me, let it.
Now this is kind of like a physics application of integrals, specifically with something called fluid pressure and force. Okay, so let's start. Fluid pressure and force. So I'll write it, fluid pressure and force. Okay, so I'll draw a quick diagram. This is actually in your textbook, but I'll explain it here, just so you get a better visual. Okay, so let's say we have some kind of container and then there's water on the top. Okay, and then the way that they have it, this is the easiest way to explain. When you have like an object with flat sides. Okay, so basically, at a certain height, at any given height, so let's say this height here that the top is at is y equals h. Okay, so first of all, to clear things up, the water level is equivalent to y equals 0. Okay, the h in this case is measuring the depth. So how far is the point that you're evaluating the force at? How far is it beneath the water line, which is 0? Okay, so this distance here is h, or y, however you want to think of it. So at a certain water level, or depth in the water, the object is going to feel a certain force. Okay, so then let's say down here we have this level of the bottom is y equals h2. So this is like h1 and h2. So these are different depths. Okay, so the top of this box, of this rectangular box, is going to feel actually less of a force than the bottom, or less of a pressure force, something like that. Because it, as you know, if you've been swimming or diving or anything like that, the more water that you have on top of you, the more pressure that you feel. Okay, and then so that holds true for the top and the bottom. And then as you see, as you move along the, if we're measuring the force on the side of the box here, it's going to be changing pretty constantly, because the top of the side here, that's at a pretty shallow depth. And then as you move down, you're going to feel more and more force. Okay, so the pressure is going to be changing on the sides here. Okay, it's going to be getting greater and greater and greater as you move down. Okay, so a couple things about fluid pressure. Number one, it, as I've been explaining, is proportional to the depth. Okay, and again, depth is measured from the water line, which is the top, which is equivalent to y equals 0. And then number two, fluid pressure exerts, is pressure. Okay, so it exerts a pressure on all sides of an object. On all sides of an object. And then this part's important, which is perpendicular to the surface. Okay, so for example, on the top side of the box, perpendicular direction would be straight downward, right? So it'll feel pressure in this direction. And then as I drew on the side here, so it'll be feeling pressure directly from the side because that's perpendicular. And then on the bottom, it'll be feeling a pressure upward. Okay? All right. So now to give you some formulas. So fluid pressure, P, is equivalent to, and I'm going to write like a fancy P thing to differentiate the two, times G times H. Okay, so this P, that just means your pressure, so fluid pressure. This P, the fancy P, I guess, that is your mass density. Ooh, what happened to the Y there? Mass density of the fluid, and this will be provided for you. This will either be provided for you or it will be the variable that you have to solve for, the unknown. So G is the acceleration caused by gravity. So this is a gravity constant, which is equivalent to 9.8 meters per second. squared, approximately. And then h is your depth. So this is your level, or how far are you beneath the water line. Okay? So then, another important formula is that pressure, or I guess that's a small p. So pressure is equal to force over area. And if you've taken physics, this should sound familiar to a certain extent. So this is your pressure. Pressure is equal to force over area. So this basically means that if you increase your force while your area is constant, then pressure is going to go up. And that's kind of like common sense. And on the other hand, if you keep your force a constant and you increase the area, so your denominator is getting bigger, then the overall fraction or quantity for pressure is going to go down. So anyways, that was kind of a side note. All right, so now I want to go over something else. Okay, so now we have when a fluid force is on a flat surface, and it's submerged vertically. Okay, so I'm just going to draw a little diagram over here. Okay, so here's our water level, all right? And then we have, so this is y equals 0, right? And let's say we have some kind of, I don't know, some kind of shape down there. Okay, it's like a parabola. Basically, what we're going to be doing here, I'm just going to give you the formula for the force exerted on this object that is in a parabolic shape, apparently. So basically, what we have is I'm going to take a certain point and evaluate the pressure or the fluid force at that point, or at that level, okay? So this right here, what we're actually going to be doing, here, I'll try to draw it as best as I can. I'm drawing a little, well, kind of a big rectangle so you guys can get the concept. But so this rectangle here, that this horizontal distance across is going to be f of y, okay? And then, well, we'll make this f of y a, okay? And then the distance down to this top level here is going to be y equals ya. All right, so this is our depth, and this is how far across, this is like the length of our rectangle, okay? And then the bottom, let's see. Hold on one moment. And the bottom is going to be the same length, right? Because we're dealing with a rectangle, so this is f of ya. They can go on the inside or the outside. Okay, so the width, though, the little width of this rectangle, we're going to denote it as delta y, because that's our change in depth, right? So let's say we make another little rectangle down here. So that was a big rectangle on top at that level, and let's say we make another one down here. I'm trying to make this as visible as possible. Okay, so now this is, don't get confused by this y, f of ya, but now let's say this is f of yb, okay? So this is the new level, all right? So f of yb, so this is at a depth of yb now, okay? It's going all the way down here from the top of the water level. And then, so this is f of yb, and then we also have a delta y here. So basically, as you can maybe visualize, is that if we draw all of these little rectangles and evaluate the fluid force at each one, we can eventually add them all up and then get the sum of the total fluid force. So in a way, this should remind you of like Riemann sums, where the whole concept of like taking small rectangles and evaluating those and then adding up their sums. So the formula for the total fluid force is actually going to turn out to be, and this is our mass density of the fluid, gravity, which is 9.8, and then we have integral, of course, from A to B, and this is your depths. So this would be like, here it would be y equals 0, so this is like your starting point depth, so that would be y equals 0, all the way to your ending point depth, which is YB. Okay, just for that case. And then we have Y, and this is, well, I'll label them later, but that's your depth. And then we have F of Y, and then times dy. Okay, so this, again, this is your mass density. Mass density. G is 9.8 meters per second squared. Y is your depth. F of Y is the horizontal distance. Okay, so this is your horizontal distance. And dy, that kind of, that comes from the delta y's that are all going to be added up. Okay?
Nigga, I am